After like 5 minutes, and just brain like leaving.
All right, good morning. Today we're going to get into an introduction of kinetics. So if you don't have a calculator, you'll need one. It's not a graphing one. You don't need one yet today. Starting tomorrow, you will. I will have some for you. So please, some families go out and buy one. Just go get one for. It's literally for 1/3 of the chapter, and I can definitely make that work for you in general. So, but if you can find one, an 83 or an 84, if there's pluses in there and all that stuff, that's fine. Those are the easiest ones to use for this. Other ones do work. Casios and other things like that as well, they work. We'll figure it out. I might have to figure it out. It might take me an extra day on a few of them, but they do work. Okay, so, all right, today, if you don't have your notes, you need notes as well. We're going to be kind of going in and out. All I have really is an example there, and then your worksheet that only has 4 problems on it, and it's not due until next Monday. I do apologize, I do not have lesson packet 23 for you. The copier died. There's a big error message on there, so I really can't do anything about it. Busted. So we'll hopefully be able to get that tomorrow. Okay, so now let me just hit the front lights here, and we'll keep going. All right, so, I left it in my back of my room. What do all these have in common?
Expiration dates. The guy has an expiration date.
That guy has an expiration date? Technically, I guess we all have expiration dates. It's not the direction I thought we were going to go this morning, but good morning. Welcome to third quarter. I forgot to bring my milk. I still have the milk from the ice cream lab, sitting exactly where I left it from the ice cream lab. Hunter, do you want to drink it? No, I'm good. See, I won't even drink it anyway because it's whole milk. I can't handle that. When I was growing up, I'd always have big church dinners in the basement of the Black Creek, where my grandparents were, the church, and I would always get ready to drink milk because I loved milk, and I always drank like 1 or 2%, and then it was always whole milk, and every time I forgot, and it was just, ugh, I just can't handle it. Some people really like it. The milk's been sitting out. It's not past the expiration date. It is not past the expiration date. It expires in a week and a half yet. Hunter, are you going to drink it?
Will I?
Yeah.
Let's do it. I thought it was.
I picked the wrong person. I don't have it in front of you. See, it doesn't scare you. See, if you saw it.
I'd still do it.
Okay. Wrong person. Annika, would you drink it? Yes, I found you. Yes. All right. We don't want to drink it. It is spoiled, right? But it's not past the expiration date, so why is it spoiled?
Because it sat out.
It's warm.
Sat out, it got warm?
It lost all its kinetic energy.
So wrong. So wrong.
What happened?
If you didn't hear that, it lost all of its kinetic energy. It almost hurt a little. No. What does this do for us? Keeps things cold. Anything else? Fresh. But what is it actually doing to keep it cold? Well, okay, it keeps it cold. If I put the milk in the fridge, it'd been fine, right? So, things spoil, things decay. So what is the fridge doing? Can the milk go bad in the fridge?
Yeah.
Okay. So the milk can go bad in the fridge or without being in the fridge. Apparently, it happens a lot faster out of the fridge. In the fridge, slows down, right? So we are altering the rate in which it basically is breaking down or spoiling or whatever the reaction is, okay? What this guy's doing is he's painting the Golden Gate Bridge. He's trying to slow down basically the redox reactions that are happening with the salt water and the creation of rust. He's trying to slow it down or prevent it altogether. We can wrap up, sorry, it's on the bottom. We can wrap up sandwiches and things like that, right? And they stay fresher. Why are we doing that? We are making a barrier. It's not perfect because there's still small little holes. There's effusion where oxygen can come in and out, and that's what the reaction is happening. But it does keep it fresher. So we can alter or we can delay rates of reactions. And that's what this chapter is about. Now, it's not about food, sorry. Food sciences, Mrs. Mayer, next year. Go for it. But it's about rates, and that's what we're going to kind of talk about today. So I don't know how much of you, some of you might be like, May 29th, like I will not. I'm more of a plus or minus 3 to 4 person kind of day, because I figure if that's exactly the day that it expires, in this day and age, they would have a lot of lawsuits if something would go wrong the next day. So, like what if they are a plus or minus 1 day? So I figure that they play it safe. Maybe I'm totally wrong on that, but who knows? All right, so you don't have to write any of this yet. A car, that is a sweet car, is driving down the road, and if it's traveling 200 miles in 4 hours, can you tell me anything about that? Did I ever play the, I think I did, didn't I? The 80 miles per hour video? Didn't I in this?
No.
Okay.
Do it.
You probably don't have time for this, but we will anyway.
Alright, we're traveling from Logan to Boise, and I just proposed a math question to my beautiful wife, Chelsea. And the question, very difficult to calculate, is if you are traveling 80 miles per hour, how long does it take you to go 80 miles? Okay, what do you think, Chel? Let's go through the process. What do you think?
Well, if I run the mile in about 9 minutes.
Wait, what about the tire turning thing you were talking about? You think that affects it?
Well, I just guesstimating probably about, it turns about 400 times in a mile.
That's just calculate, like guessing calculations?
Yeah, I don't know how you would work that out.
It'd be tough.
Yeah, so, I don't know, because if I run a mile in like 9 minutes, then, I mean, but that's when I'm out of shape. When I'm really in shape, it's like 7 minutes is when I'm like really in shape. And that takes me a mile. And we're going 80 miles. I'm running at about probably 10 miles per hour, if that.
Yeah.
And that's pretty fast for a human being, I think. But, I mean, it's got to take at least like 58 minutes or something
58 minutes? It's pretty close.
to go 80 miles.
Do you want to know what the answer is?
But,
Think about 80 miles per hour.
yeah.
So how long does it take me to go 80 miles if I'm traveling 80
You're
miles
driving
per
fast. You
hour?
are driving faster than a minute a mile.
Yeah, totally.
So I would whack 80 in half, and that's 40. Because I mean, you're probably going 2 minutes a mile.
Just whack it in half.
Well, depends on. I mean, some cars' tires turn faster than others.
Yeah, definitely affects it.
Because I mean, I think a truck probably is slower because it weighs more.
Mm-hmm.
But I think it also matters if your car's a stick or automatic.
Okay, John,
What?
think about the term miles per hour.
MPH.
MPH. So if I say I'm driving 80 miles per hour, that means I'm going to go 80 miles in an hour.
No, you are not, because you are driving faster than a mile a minute. I can run 1 mile in 7 minutes, and that's a 10. Okay? So I mean, that's booking it too.
Okay, so if I'm going 60 miles per hour,
Then it'll take about 30 minutes. I would just cut it right in half.
I'm trying to explain the answer, but
Well, you are not making sense because I make sense, you do not make sense. My car's tires may be they're kind of a little flat, so they may not go as fast as like a police officer's tires that are full, but
okay, Chell, the
my
answer.
tires are turning maybe, I'd say about 400 times per mile.
Okay, I'm gonna tell you the answer. You ready for
No,
the
they gotta
answer?
be like 1,000.
You ready for the answer? The answer
You don't
to...
know the answer.
I do know the
You
answer.
can guesstimate just like I guesstimate.
I guesstimate. Science. I'm using my own term. Okay, chill. The answer to the question, how long does it take me to travel 80 miles if I'm driving 80 miles per hour? The answer is 1 hour. Your guess was close.
So say you drive 60 miles per hour at 60 miles. You want to go 60 miles at 60 miles per hour. Is that an hour?
Yep.
What about 40 miles at 40 miles per hour?
Then you will go 40 miles,
No,
1 hour.
You cut that in half. More than a mile a minute. Okay, what's time?
Alright. They made national news out of all these talk shows on that one. So, just say they were newlyweds, and she was not very happy with him for posting that online. So, we're talking about if you're traveling 200 miles in 4 hours, would this be safe to say? Could you say this? And those are miles? Could you say that? Maybe? Maybe. No. Obviously, like, well, yeah, but I stopped to get some chips, or I ran out of gas, or my tires were rotating 1,000 times because they were flat. I don't think. But this is not the way we can think about reactions, because this is very consistent and very constant. And that's what we're going to look at today, is how does a reaction actually behave. It's going to behave a little differently than this, okay? So, that being said, you'll want to put this in your notes, okay? I've tried to eliminate as many notes as possible, but some of this, there's no way to get around it. Okay, so we're going to deal with this reaction to try to help describe what is happening, bless you, in kinetics, in a reaction, in chemical reactions. So here are my reactants, or reactant in this case. Here are my products, okay? I hope we agree. If we don't get to this point, it's really hard to move forward from it. We have to deal with two sides of an equation. We have the reactants and we have the products. Reminder that brackets mean concentrations. If you need to write that in there to remind yourself, brackets mean concentrations. Those are not parentheses. Those are brackets. So I'm dealing with a concentration. So the concentration of my reactants as it's going forward will decrease, and my products as a reaction is going forward will increase because it's transferring from one to the other. Kinetics deals with how fast this happens. How fast are we losing them, or how fast are we gaining them? Okay? So, some of it I've already written, just to save some time. So, like we were talking about MPH, that's a distance over time. Well, instead of talking about distances in chemistry, what we are going to be talking about in the first part of this, there's two parts of kinetics, concentration and time. And I know this looks like we're using them at the same time, but it's going to be the rate dependent on the amount of time. So this is called the reaction rate. The rate of the reaction is the change in your concentration over the change in time. Okay? And it can be positive or negative. Why? Because we could be losing or we could be gaining, right? If we're gaining, it's products. If we're losing, it's reactants. So that's an important thing to be able to interpret. And I'm going to be drawing some things on the board as well, just so you know. We'll kind of be going in and out. I do have one demo to do today. Hope it works. A is just a generic compound. So I could have written NO2, it's anything. I just didn't want it specific to that. Okay, so we're going to be dealing with this a lot, where you are talking again about the change in your concentration over the change in your time. So let me just show you an example. You don't need to write down this whole table or anything like that, but let me just show you kind of what we could do in the beginning of this. We're going to get more specific really quickly, but I'm going to move forward. So don't worry about all this. This is in your book. I do want you to notice something. Okay, as time is going on, so just check this out. 0 to 50 seconds, and then it's intervals of 50 seconds. And what you're noticing, my laser's dying here. We start with an amount of reactant, and we have 0 products, right? Every reaction, and this is the key observation to start with. We're going to get high tech here. Every reaction starts with reactants, and should make sense, at least in the beginning, there are no products. Okay, so we have to keep that in mind in a minute of how can we really describe reactions. But notice what's happening. If I go back to my car, it was 50 miles, 50 miles, 50 miles, 50 miles. What's happening, and you can look at any one of these, what's happening as I go every 50 seconds to the concentrations? They're decreasing, right? And the rate in change, right? Like this is getting consumed. These are going up. These are going up, but it's less and less and less. And there's a reason behind that. And some of it we can't answer this chapter, but other things we can. So what I would like you to write is, and actually you don't have to necessarily write this if you don't want, but this is how I figured this out. I just use this data right here from 0 to 50. If you just want to see at least what I did here. So what I did is I did the reaction rate. So it's the change in NO2 over the change in time. So at least see it, but if you want to, it's not the whole table, I'm just doing 0 to 50. I took the concentration at 50, I subtracted the concentration at 0. I took the time at 50, I subtracted 0. I need you to physically be able to see that, okay? That is a reaction rate. I just did this as a subscript. I need you to understand some just notations. It's a really easy way. Remember when we used to, can't remember what specific thing we were doing. I know when we were doing some gas laws and things like that, we would do a subscript of the compound of the gas that we were testing at that exact time, so we could keep it straight. Shoot. Awesome. I fooled around with this the other night. Now I'm paying the price.
Why is it negative?
Why is it negative? Why is that negative? Why is that negative? Anyway?
It's decreasing.
Decreasing. The rate is decreasing. I'm losing my NO2 because it is a reactant and not a product. So, I wrote added, consumed. It's being consumed, okay? You have to add that in there, though. That's what the added means, by the way. Like that, you have to actually include that. But just like thermal, the sign is just telling you direction. So sometimes the sign might not be there. You need to potentially interpret it. Okay? You got to be careful. So this, no matter what, you need to understand though. Reaction rates decrease over time. And it's a big deal when we start getting into this. We need to understand the meaning behind this. It will help you kind of execute things more efficiently. Okay? So we're going to talk about what a rate law is. Today is about writing some laws and it's not the way it sounds. But what is a rate law? Hold on, sorry. So actually, don't write rate law. That's where I'm drawing for a second. So, we want to just make a little graph here quickly. And we're going to be doing more of our sheet in a minute, but all right, what if we had a graph that looks like this? So I have concentration on my y, time on my x. Okay, so shoot, I need to rewrite this equation. I'm going to just write it above. You should, if you didn't write it down the first time. So, as the reaction's going forward, what we saw was that NO2 is decreasing. Now, it doesn't have to be perfect, but just as long as it mirrors kind of what I'm doing here. Eventually, what you're going to notice, it will level off. And that's where we'll lead into the next chapter. Eventually, you'll actually start remaking the reactant. like the products will start to combine or start to interact and actually start to create the reactants again, or it just slows down and it reaches a natural equilibrium regardless. Okay? Well, if this is a rate, and this is showing, and we'll talk about rates in a second and how I use this with the graph, mole ratios. However much I lose of this, which one is equally gained as a product? Which one is created in the same amount? The NO, isn't it? Mole ratios. Okay? So, the NO, what you need to do, start from 0, but then you want to mirror the same shape as NO2. Okay? Notice I started at 0 because when I'm starting, a product has 0 for the concentration. So, how much does the O2 make in comparison to anything? How could I describe that? Half of what? Of the NO, because I'm still producing it. So, I want to make it look something like this. Oops, leveled off a little harsh. Make yours a little nicer than mine. But the rate of production, or the amount, will be half. It will be half. Okay? Well, that's great. And over time, if I have enough information, I can figure all this out. But what if I want to find out how fast something's being produced or how fast something's being consumed right now? Like right at this point. What if I want it right then? Like I can't do a slope, so I need to find an instantaneous rate. Some of you are about to groan. Because what if I do this? What is that? Luke, what is that? Tangent. That is a tangent line. You're like, no. My worlds are colliding. That is perpendicular to an exact point. Okay? And what that does is this tangent line, believe me, whatever you've done in any of your math classes will not be close to the level, meaning it's much higher in the math classes, is what we're doing here. The rate will equal negative slope of that line. It's more about an idea that we're going to be utilizing, okay? So make sure you box that, please. So, one more quick thing on this, and then we'll move on to kind of rate and rate laws. So what about comparing rates? You'll have to do this on your packet, which you don't have today, but... So, if I said the rate of NO2, now I'm not saying that there's 2 in front of it, I'm just saying that's the rate of NO2. How would it compare to O2 and to NO? Now be mindful, I'm comparing it with this. I'm utilizing this first. So, how does the rate of this, what does this have to do to equal NO2? Ellen?
Wouldn't you just flip NO2 for NO?
Okay, so act like NO2 is NO? Is that what you're saying? Okay, so then if NO2 is NO, what's the difference with NO and NO2? I mean, NO and O2.
O2 is half of NO.
Okay, so if it's half, but I'm saying I'm comparing this, would this be double that? I need twice the amount of this to equal that.
Yes.
And it needs to be opposite. These are just some ideas that we're gonna use. I'm just kind of previewing them to you. You understand? I need double this, and it needs to be flipped to equal that. I know you could say, well, wait a minute. You said this was 2, this is half of that, and this is 2. Yes, but what if I was saying, how do these relate to this 1? This has to be double the rate, and it's got to be negative. What about this one? It's the same rate, but it's opposite. What's confusing, you're like, wait, but that's the one that's being produced. That's not the one being consumed. I'm relating them. So these are my products. This is a reactant still. Please keep it clear. You could relate any of them to any of them. Like if I related O2 to each of these, then this would be half of that. This would be half. Because this is, the other ones are double that. Okay? So those are some things that we might head down in that path. Again, this hasn't all come together yet. It's like I don't even know what I'm applying. Just give me a little bit of background so we can get into some of the things. There's two kinds of rate laws that we're going to be studying. So here we go. High concentrations. They provide greater opportunity for molecules to collide. So what we are looking for is really important because this can be in a free response question. You need to understand that if it's a low concentration, it's a more difficult or a poor study for kinetics, because kinetics is the study of how fast the rate of a reaction is. Reaction, however you want to still imagine this as chemistry, chemistry has to actually have interaction. Molecules have to actually touch. They have to collide, and they actually have to collide in the right way. They can't just bump into each other. They have to bump into each other correctly for a bond to be created or to be broken. So, high concentrations provide greater opportunity for molecules to collide. So here's an example. A plus B equals C. We care about the reactants. And this is really important for you to understand. Because every reaction starts with reactants. The beginning of a reaction is when you have the greatest concentration. But you also have zero products. So you don't want to study products. You want to study reactants. Because once products form, reaction could start to reverse. So we want to study it as quickly as possible. To avoid issues, we study reactions at the beginning. Like right away. That's the fastest rate. We saw that. Rates slow down as it goes. If we study it right away, we can study how fast a reaction is going. Now, obviously, maybe it matters 7 hours from now. I want to know how fast a reaction is going. Okay, that's a different conversation, which we can apply. But that's later. That's an integrated rate law. We're not doing that today. Rate depends on the concentration of reactants. I think I've already said it once. If not, that's all that's going to matter for us. We want to study the concentration of the reactants, not of the products. All right. So, let's learn how to write these. It's like a 290.
That's all I'll do today. So, like, I mean, I have a rough script.
All right, here we go. We're going to label what all, here's what a rate law looks like. So a rate, we just learned that, is a concentration, change in concentration over change in time. Okay. We're going to have a K. You know what? I'll just write it all out first, and then I'll label it all. Right. So, K is a rate constant. It is vital. Every time you write a rate constant, there's a point for units. Got to have units right, okay? Big deal. These are going to be, whoops, wrong. Green, anyone?
Or your
Thank you. These are my reactants. And these are what we are going to call the order. And what this is, it's how rate changes with concentration. Just so you know, we'll talk about it in a second, but overall order, actually overall reaction order, is X plus Y. You had to add them up, and we'll talk about that right now. So we still have more to do. We'll get this all in. But some reactions, and you're going to see an example about it in a minute, depend on concentration. So, 2 beakers. I'm going to roughly put the same amount of zinc in each. One of these touched some acid, so that'd be interesting. All right. I have 3 molar HCl. And I stock solution 12 molar HCl. Not a lot, but. All right, we're going to see, I'm going to put hydrochloric acid with zinc, so HCl plus Zn. It's a single replacement reaction, right? It's going to make H2 gas, all right? But doesn't matter on the concentration of the rate, how much faster. Certain reactions it doesn't. Some it does, some it really does, and it affects it. So hopefully we'll see based on the balloon, but I haven't thought this out. I'm not sure. Okay. I got it. I'll put in the zinc after. So.
would the 12 molar melt through plastic? What is it in that?
Not hydrochloric acid as much. I got it. All right. I'm going to try that, but I'm a little worried because they're sharp. here. Oh boy. This is what we're going to do. It doesn't really matter. You're going to be able to see this. I'm going to put this one in first because it's slower. I'm just assuming. Gloves, get out of the way. As you can see, oh jeez. And as you can see, concentration matters. I don't really know where to put this.
Wow.
So, in this case, the order or concentration matters, and we could figure out the order of the hydrochloric acid to this reaction based on the concentration. So, I'm going to do something kind of cool here. That was totally you. The other one's still doing nothing. All right, we're going to light this. So, a little hydrogen for you. A little nice slow. All right, so let's talk about this though. We're doing great on time. Going back to rate laws now. So, here we go. Let me see if I can, I'm going to write it over here. Hopefully you can see this. So if I have concentration of A, okay, and I have the rate reaction, or reaction rate, so if X was 1, so it's just like rate equals, if you're just thinking this, rate equals K and then A to the X. So how does this affect? Based on the order, how does that affect my overall rate? If, hang it, if the concentration doubles, what happens? Well, it would be 2A to the first. So I would double it, but it would be the first. It means it would double. Like, a first order is a direct relationship. If it triples, just showing you like the concentration of A would triple and it'd be to the first, so it would make sense mathematically that the rate triples. So, okay, I double the concentration, hey, it goes twice as fast. Like most people are like, well, duh. Well, the thing is, a lot of chemistry doesn't work like that. There's other kinds of things that can happen, okay? Like, what if it's considered a second order? What this means is that the reaction rate is more dependent on my concentration. Okay? More dependent on my concentration. So for example, again, if this doubles, I guess I was going to write then, if that helps you. Like if it doubles, then that happens. If this doubles or triples, so then what? I still have 2a, but now it's to the second. I still have 3a, but now it's to the second. So what happens? If I double my concentration, you can imagine concentration is 1 or whatever else, or 2. So if it was 2 and then 2 times 2 to the second, what happens? It quadruples. What does this one go up as? You don't need to know the phrase, just how many times. It'd be 9 times. So right there, look at how quickly this happens. If something would be considered second order, that's what would happen. Just a couple of quick ones yet, and then we got to get to an example. Here, you know what? I'll just get the 0 order. Like 0 order, it can be a 0. I'll show you this last one, and then we're going to get into our example. There are things called 0 order reactions, and what those are is that regardless how much I put in to a reaction, the rate of the reaction will always be the same. Like what? Like if I double it, it'll speed it up. No, apparently not. Well, cut it in half, it'll slow it down. The concentration apparently in these reactions are independent of well, the concentration doesn't have any effect. It's just, is it there or isn't it? Okay, so the rate would be unchanged. We could do third order and all that other stuff, but we're not going to be running into those nearly as much. So I want to do an example. So if you want to grab your sheet, please. We're going to end with this, and this will help you with Kinetics 1.
How do you determine what order it is?
We will. I'll show you.
Oh.
We're going to do all of that. Yeah. Good luck. Goodbye. Have fun. No, we got to go through it. Got to figure out how this all works. All right. So we are going to answer some questions on your sheet specifically. So please feel free to write on it and everything else. All right. So here are 3 reactions that were done. And here's the equations on the top. You're taking ammonium, and this is a net ionic equation, so we don't know what the other ions are, but the players that matter are ammonium and nitrite, and they're reacting and making N2 and H2O. Really don't care about the products. I care about the reactants. So in experiment 1, I did 0.1 molar and 0.005, and found out that the initial rate, meaning right away, the initial rate was molarities per second. It was 1.35 times 10 to the -7. These numbers aren't going to mean a lot to you. It's more about what we use them. And then the second and the third experiments. Okay, so letter A. It says, order of each reactant. All right, so this is what we need to do then. All right, we need to find the order. So let's do here. We'll just do the A first. Let's worry about the first one, so NH4. So let's talk about that one. So you don't want to write too large, but I've given you enough space. This is what you want. In science, in general, when you are doing an experiment and you are studying something, the thing you are studying is the only variable that should be changing. Right? Everything else should remain constant. So I want to look at these 3 experiments, and I want to isolate NH4 plus by making sure that NO2 is unchanged. And the reason why is I want to know, by altering this, how does it affect my rate? Well, if I change them both at the same time, I have no idea what effect my one ion has on the rate. Okay, so I want to find something that changes in this ion, but is unchanged in this one. So what 2 experiments? I need to look at 2. What 2 experiments can I use to study this, Kevin? 2 and 3. 2 and 3, that is great. So I'm going to take, and you won't necessarily have to write it down this crazy every single time, but I'm going to take experiment 3 over experiment 2. And the reason why is that the NO2 is unchanged, right? But the NH4 is not, okay? So what I have here, I'm just kind of trying to do labels here so you understand what I'm doing, is I had 0.200 molar over 0.100 molar. Okay? Over here, I'm going to have my rate. Okay? And I had, got to do in the same order, 5.4 times 10 to the negative 7 over 2.70 times 10 to the negative 7. If they have the same exponents for math, do I need to worry about them then, mathematically? Like dividing stuff, right? Those are, like I'm just basically taking 5.4 divided by 2.7, correct? Okay, so trying to make math easy for you here. So 0.2 over 0.1, that's 2. I need you to understand what this is saying is this is 2x equals, and this is also 2. So when I double the concentration, my rate doubled. So what's the order? What happens? What is this? This is a first order because, and this is where you need to start filing under how to understand this. First, just mathematically, this would have to be a 1 to make this true, right? 2 to the first equals 2. But when I doubled this, this doubled. Like it was a direct, even relationship. So this is a first order. So NH3 is a first order. And we're going to go through this whole thing. We got 6 minutes yet. We're going to be perfect. Let's talk about the other one quickly. So what do I have to do with that one? What experiments? We'll go a little bit quicker. 1 and 2, and I think I'm going to do 2 over 1, I think. Yep. So I have point. Now you're going to be like, oh, this looks the same. Well, let's find out. It might be, it might not be. And every problem is going to be different. So that doubled again, it looks like. Shoot. I thought I had a different problem. It's all right. So it's another first order. Yeah, I didn't want that. Let's hold on for a second. What would have to happen, just so you understand, because you're going to run into one really quickly, for this to be a second order? Okay?
Rate would have to be 4.
Good. Right? The rate would be a 4 here, because then you go, oh, 2 to the second equals 4. Oh, now it's a second order. That means when I double it, the rate like quadruples. Oh my gosh. So that's more dependent on it. Okay?
Did you put them in that order, like 2 over 1, just so you didn't have to do with negatives?
Yeah. Well, I wanted a positive value, like a great a whole number. Yeah. How do I get a 0 order? What would this become? It'd be 1, because the rate would be the same. Wait, I doubled the concentration, but the rate did nothing. Oh, it's a 0 order. Okay, so what does that all mean? Well, first off, I got first order, first order. I'm doing this step by step. It says write the rate law equation. What does that mean? Simply this. You write rate. I think I did have a balloon from acid. I'm getting weird. Something's happened. And by the way, this was the concentration of NO2 minus. Right, so we write it like that. Now, I'm going to put a 1 there, but usually if there's 1s, that you don't write them. Okay, but that's where that goes. So for example, this is my first order. If it was a second order, you put a 2 there, for example. That's where they go. Right. Well, what's the point of all this? It's actually to get to the actual meat of it all. Is trying to figure out how fast something goes. Again, after I finish these 4 things, you're going to be able to answer all the questions on your worksheet already. So we're doing really well on time. It says, C, rate constant. So I got to figure out the rate constant. Okay, this is how you do this. You pick an experiment. Just pick one. Okay, now I know the order. I pick it. So I'm going to pick experiment 1. I always just pick the first one. So that's the rate. I plug it into the rate. So this is 1.35 times 10 to the negative 7 moles over liters seconds. And we'll talk about units in a second. That's also just big M over S, if you want to do it that way. Equals K times 0.1 molar times 0.0 0.050 molar. And those are the first. So, help me out, calculate that. What is that? Actually, you know what? Due to time, I'll do that for you. So you multiply it, divide that under here, and K will equal 2.7 times 10 to the negative fourth, but I need a unit. So, if you look at this, it was molarity times molarity, so that's molarity squared, right? And on this side, it's molarity over seconds. So I got to make it equal this, right? So basically, I need time. And if I have molarity squared, but I only have molarity here, I need to get rid of one molarity, right? And that's what I need. I'm going to give you a hint how to do this eventually, but this is how it'll look. Molarity flipped over would look like this. It's liters over moles. And then I just put in the time. I'll give you the hint. And you may not process right now, and I'm really close to time here, but I'm going to help you out as much as I can. For this unit, it's always one less than overall order. Meaning, if it was a third order unit, would be liters over moles, and you square that because this is one less. And then you just put in the time. If it was seventh order, it'd be liters over moles, and they'd both be sixes. You want one less, and you have to just flip the molarity. And we're going to practice that a lot, but that's what you're going to have to do. I know we're really close, but we got to just finish here. D, sorry. Then how do I do this at the ending? Now I can figure out anything at any time. So what I do now, what is the new rate? The rate is you simply put in the constant, because that never changes. And then you just put in your new two concentrations. And those are both 1. So I can figure out the rate at any point within a reaction now. And that's the whole goal, is what's the final rate of any concentration at any moment in a reaction. So this is going to be based on concentration. Okay? So, start working on Kinetics 1, please. I will get you lesson 23 tomorrow. Okay? Yes. Please head out the other direction if you guys can.
Why is it so loud?
Yes. Then we have anatomy. Oh, no, we have lunch.